Hello again. Want to take some time to review for Monday's exam. Want to make sure we're ready for Monday's exam. Now then, a couple things important here. I'm going to do a video which will be available Monday morning for homework 4. Homework 4 is due by midnight on Sunday. The reason for that is I want you to finish homework 4 up. I'm going to give you a little short review for homework 4 on Monday morning so you can use that to prep for the exam. And then I'll open the exam right after that so that you'll have 24 hours from the time I open the exam up to take the exam. So that means if I open it at 8 o'clock on Monday morning, by 8:15 we'll be through the review for the homework. You'll have from 8:15 Monday morning to 8:15 Tuesday morning to do the exam. 24 hours. You'll have a time limit, though, once you start, of 120 minutes, 2 hours. Should not take you 2 hours to take this exam. But you've got 2 hours. Take your time. Read the questions carefully. I got some slides that I put on Blackboard, so if you want to follow along with the slides in the video, print the slides out, whatever you want to do. But I want to go through all the materials to make sure that we're all on the same sheet of music and looking at the same stuff from the same level of importance for Monday's exam. The exam will be a lot like past Monday's exam. Fill in the blank, short answers, multiple choice. There'll be some problems because we've done some calculations this week. So there'll obviously be some problems. We're trying to take statistics, do a sample, and infer something from that sample about the population. There's 150 points, just like the last exam. There's 25 questions. Now we got 8 different topics. There's 25 questions. It can't be too in-depth. By the time you do some of the calculations, that's going to take up a lot of time, a lot of space. 6 points apiece. Do not leave them blank, please. Do not leave the question blank. If you don't know the answer, make something up. If it makes me or Alice or Amber, the 2 TAs, smile, you'll get some points. It's better than no points at all if you don't answer. So if you don't know the answer, make something up. Seriously. So the topics we've looked at since the last exam, we looked at quality, which is really based a lot on statistics. We looked at frequency distribution, descriptive statistics, probability. We looked at confidence intervals yesterday. We looked at correlation this morning, regression this morning, and hypothesis testing this morning. 8 topics, 25 questions. It only leaves about 3 questions per topic. Doesn't leave a whole lot of room to get deep in the weeds. This isn't a deep in the weeds kind of course. This is a survey course. Do you understand the concepts? That's what we're trying to do here. So we looked at quality on Tuesday. What is it? Quality is fitness for use as designed to be used. That's a critical caveat. You can't use my laptop as a hammer. It won't work. I can't carry my desktop everywhere I go. It's not portable. So it's not a very good portable computer. It's fitness for use as designed to be used. It's defined by the customer. I can tell you as the manufacturer, this is the greatest product in the world. And you buy it and you try it and you go, that's a piece of junk. So quality is defined by the customer. We looked at some gurus of quality from the past century, and we're still using their work today. We looked at Duran. Duran said in the 60s that quality should be a strategic initiative. Looked at Feigenbaum, who said that everybody who works on a product is part of that quality management team. From the folks who mine the materials, that source the materials, that make the materials, that deliver it. They're all part of the quality management team. We looked at Stewart all the way back to the 1920s, 100 years ago, with his plan, do, check, act cycle, which is the foundation for most continuous improvement programs today. And it's also the foundation for his work. It's foundation for most statistical management programs today, statistical quality control. We looked at Dr. Deming, who went to Japan at the end of the 40s to help rebuild their economy and taught them statistical quality control, things he learned from Sheward. He established 14 points, which are still the foundation for many quality management programs today. We looked at the cause and effect diagram, Ishikawa diagram, fishbone diagram. Call it whatever you want to call it. It's a great tool for looking at a quality problem, look at those 6 key areas and backtracking and finding the cause of my quality issue and fixing the cause. We can do a cause and effect diagram right now. What's the cause of all the issues here in the country? And let's track it back and look at what's causing the problem, and let's fix the problem. Quit talking about it. Quit putting Band-Aids on it. Let's fix the problems. Let's use the cause and effect diagram. We could do that and look at it. We looked at ISO 9000, an international standards for quality management systems. We looked at ISO 14000, an international standard for environmental quality systems. We also took a little look at the cost of quality from Crosby's Quality is Free. And we had FedEx's 110-100 rule with quality. We looked at the cost of good quality, internal operations. The cost of good quality is designing a quality product, building a quality product, sourcing quality materials, delivering a quality product, doing some statistical sampling to make sure I'm making a quality product. And then we looked at the cost of poor quality. Internal to the organization, scrap, rework, process downtime. We looked at the cost of poor quality outside the organization once it gets in the hands of the customers, that 100 piece of FedEx 110-100 rule. Warranty work, liability, lost sales, recalls, all those things add into the cost of quality. And what Crosby was saying was those costs of poor quality are so high that the cost of good quality appears to be free. We looked at frequency distributions and creating frequency distributions. We had our example from the newspaper. We had clear-cut categories, 0, 1, 2, 3, 4, 5, 6, 7. And we had the number of observations or respondents for those categories. They gave us a frequency distribution. From that, we get relative frequency, which is simply the number of observations for a category divided by the total number of observations. We looked at how to create a frequency distribution table if I am not provided those clear-cut categories. We had some steps. Step 1, I've got to raise 2 to some power, 2 to the k, raise 2 to some power to be greater than or equal to my sample size. So if I've got a sample size of 100, I've got to raise 2 to the 7th power, because 2 to the 7th is 128. That tells me if I've got 100 data points, I'm going to have 7 classes of data to make sure that I'm getting good breakout of my data to make some good observations. Second step, I got to find the width of each one of those classes. Largest value minus the smallest value divided by the number of classes. Now, if that works out to a fraction, any decimal, round it up to another number. Just make sure on the exam, since that part will be hand graded, make sure we know what you rounded it up to. That may impact your frequency. Step 3, we find the lower and the upper boundaries for each group of data. Group 1 is going to start with my lowest data point. So in the example we had in class, the lowest data point was 35. And each group was 210 wide. So the first grouping is going to be 35 to 245. We're going to add 1 to the upper boundary when I start the lower boundary for the next group, because I don't want them to overlap. I want them to be mutually exclusive. I'm going to do that for all of my classes of data, like we did in the example in class. And then step 4 is to find the frequency. How many data points fall within each one of those groups? I can get the relative frequency from that by taking the observations for each group, divided by the total number of observations. So in our example in class, in our first group of data, we had 9 data points fell in that group. That's the frequency for that group. We had 72 data points, so the relative frequency is 9/72. That's it. We looked at descriptive statistics, trying to describe the data, taking my sample data and describing what it really means, taking that data and turning it into information. Now, in business, we've been using the term big data as the buzzword for about 10 years now. Let me tell you something, folks. We've got big data. What we really need in business, and almost every survey of CEOs verifies this, what we really need is usable information from that big data. So we're trying to take this data that we've got, and we're trying to make it into usable information. We're trying to describe what we've got. So we looked at the mean. Simple average. Take all my data points, add them together, divide by the number of data points. That gives me the mean. We looked at the median, the exact midpoint. Put it in numerical sequence. If I've got an odd set of data, I find the exact middle point. So if I got 9 data points, I find number 5. Now I've got 4 above, 4 below. I've got 10 data points. Now I find 5 and 6. I add them together and divide by 2. Now I've got 5 above and 5 below. The median is not impacted by outlying data points, as is the mean. One extraneous data point can really skew your mean, but it won't change your median. Back to my example in class of my realtor and trying to impress me with the value of the houses she sells. We looked at the mode. We said that every set of data is going to have a mean and a median. Not every set of data will have a mode. I may have no mode. I may have one mode. I may have multiple modes. It's just the most commonly occurring number in the data set. We looked at the standard deviation. And we had 6 steps there in the slide deck and in the example in class. We had 6 steps to go through to get to the standard deviation. To understand the calculation in Excel, because we said I can get the mean, the median, the mode, standard deviation by going to data analysis, descriptive statistics, put in the range for my data, put in the output range that I want, click on summary, click on OK, boom, there it is. So use that. But remember, the difference in those 6 steps in step number 5 was the difference between a population, standard deviation, and a sample. And Excel gives you the sample. If it is a population in step 5, I've got to divide the sum of the squares by the population size. So make sure you read the questions in the exam carefully. Is it a population or is it a sample? Because if it's a population, you can't use the Excel data from the data analysis because that's going to give you a sample and will give you the wrong number. You got to go into formulas, other statistics, standard deviation.p for the population to get the right answer there. We looked at the coefficient of variation, a great tool for comparing different types of databases. We had the example in class of the weight versus the cube for trailers and trucks. I can put it into a coefficient of variation, which is simply a percentage of variation around the mean. And that will give me a percentage of variation. And I can make some decisions based upon whether I'm looking for the higher or lower coefficient of variation. We look at the weighted mean as a descriptive statistic. Just another way of looking at the data, trying to make sense of the data. Same thing as your GPA. You got your column of quality points per grade times the grade you got, or times the number of hours. Take quality points times hours, add up all of those, divide by the total number of hours, you get a weighted mean or a GPA for your semester, for your time in the university. It's the same thing, column A times column B, add all those up, add up all of column B, divide the sum of A times B by the sum of B, that gives you your weighted mean. Just another way of looking at data, because there's not a one-size-fits-all, this is the best descriptive statistic to use. And what you're going to see in business is, and really in sports, what statistic makes me look best is the one I'm going to use. So you can use statistics from the book, How to Lie with Statistics. You can use statistics to pretty much make any point you want to make. That's why there's so many different statistics out there. So the real purpose is so you understand when somebody says, I'm using the statistics, why are they using that stat versus some other stat? Is there a better stat to use to get a better, clearer picture? Because the purpose of statistics is to make better informed decisions. We look at probability. So probability runs between 0 and 1. If it's 0, it can't happen. It will not happen if it's 0. If it's 1, it's a sure thing. Probability is 1, we'll have an exam on Monday. Probability is 0, we'll have an exam on Sunday. Anything between 0 and 1 is a calculation of the probability that it will occur from an unknown event. We looked at using relative frequency to get probabilities. So if you look back at that example we had with the newspaper example, in my newspaper example, we had 200 total people. 44 of those 200 said they never read the paper. So based upon that relative frequency, 44 over 200, or 0.22, that tells me that the probability of any randomly selected subscriber to that newspaper, the probability is 0.22, they never read the paper. We look at simple probability, the way it occurs over total number of outcomes. So we looked at my dice. Got my die here from Buffalo Bills in Nevada. I've got 6 outcomes on this die. One can only happen one way. So the outcome, for rolling a 1, is 1. It's the only way it can come up. But there's 6 outcomes. So the probability of rolling a 1 on a single die, assuming it's a fair one, is 1 over 6. Number of ways it can occur over a total number of outcomes. Look at joint probability. And again, we use my dice. So let me get my second die here. From Sam's County, Las Vegas. Now then, I've got the probability of rolling a 1 on this die times probability of rolling a 1 on this die. 1 over 6 times 1 over 6. So the probability of rolling a 1 and a 1 on 2 separate die is 1 over 36. Look at putting data into a contingency table. And I said, I prefer to do it that way. If I can put my data into a contingency table, I get everything I need to know about probability. Look at the tables we had in the slide deck, the examples. If I add up my rows, add up my columns, I've got everything I need to know to answer any kind of question on probability from that data. We looked at confidence intervals yesterday. We said we had a basic formula for confidence intervals. The idea of the confidence interval is to give us a range of values that we're confident that the true value falls in that range based on our sample. Our standard formula is a point estimate plus or minus a critical value times the standard error. That critical value times the standard error is my margin of error. That's the value I add or subtract to my point estimate for my sample to get my confidence interval. Very serious when you do the exam. When you get to the point estimate plus or minus the margin of error, stop. That's the answer. I'm going to assume at this point in your life, you can take your calculator, you can punch in 20 minus 0.45, get 19.55, 20 plus 0.45, and get 20.45. I'm going to assume you can do that. So when you get to 20 plus or minus 0.45, if that's the answer, stop right there. Move to the next question. I've got some rules for confidence intervals in the slide deck, which I think will help you when you get to the exam on Monday, looking at those to make sure I'm using the right stuff to get the right answer. We looked at three basic variations of the basic formula. The first one was if I know the population standard deviation. So I'm going to see either population standard deviation equals, or I'm going to see little sigma equals, because little sigma is the statistical symbol for population standard deviation. So my formula now is my point estimate, a sample mean, plus or minus a z-score. If I see little sigma, I got to use a z-score. It's going to come from this table right here. Common levels of confidence. Maybe want to print this off so you have it, or have it bookmarked on your computer so when you get to the exam, you've got this. Because everything you'll need for confidence levels comes from this sheet right here. If it says population standard deviation equals, or it says proportion equals, my critical value comes from this table right here. No calculation necessary. So I've got my point estimate, a mean, my sample mean, plus or minus my critical value, my z-score from that table right there, times the standard error, which is the standard deviation, divided by the square root of the sample size. So I need to know sample mean, critical value, comes from the confidence level, percentage. I need to know population standard deviation, and I need to know sample size. 4 things. If I know those 4 things, I'm good. My steps are the same for all 3 variations. 1, write down the formula. 2, write down what I need to know. Plug in what I know from the problem. 3, take that, plug it into the formula, it solves itself for you. It's literally. And when I do the answer key, that's how I come up with the answer key. Because that way I know if I follow those steps, I get the right answer. It may be a 95% confidence interval, so I'm only 95% confident that the true mean falls in that range. I won't be 100% confident when I do the answer key to give to the TAs, I got the right answer. So I go through those 3 steps every time. You got 2 hours, take the time, take your time. Write down the 3 steps and do them. So let's look at an example. I've got a sample of 11 metal rods. We got a normal mean resistance from the sample of 2.15 tons. Our population standard deviation, there's the keyword, it's in that slide right there. There's the keyword. The population standard deviation is 0.3 tons. We want a 95% confidence interval. I know all 4 things I need to know. I've got my sample size of 11. I've got my point estimate, my mean of 2.15. Got my population standard deviation, 0.3. I've got my sample, I got my confidence interval level, 95%. Look at this table here. 95% says 1.96. I've got 1.96. I've got the 4 things I need to know. I write down the formula. I write down those 4 things I need to know. I plug those 4 things into the formula. And when I do that, I come up with an answer of 2.15 plus or minus 0.177. I am 95% confident that the true mean resistance of these rods is 2.15 plus or minus 0.177. But I'm 100% confident that's the right answer. So we'll make sure that you're 100% confident by following those 3 steps. Second variation we looked at is if I see the words sample standard deviation equals or little s equals. I see little s. Next thing out, that's a little t. I got to use the t table. I have got to use this table right here to get my value. Now, again, quick review of this is I've got my, down this column here, the left-hand column, I've got the degrees of freedom. Degrees of freedom is sample size minus 1. Across the bottom of this table here, you look at this table that I've given you, across the bottom is the confidence levels. Don't worry about the stuff on top. I want to find my intersection of degrees of freedom and my confidence interval percentage. That gives me the critical value. This is the only exception to the Z rule for confidence intervals. So now my formula is my point estimate, my mean, plus or minus my t-score, again from the t-table, times the standard error, which is now the sample standard deviation, divided by the square root of the sample size. So I got an example in the slide deck for this one too. So take a look at it. I see little s, so I know when I see little s, I've got to use the t-table. I've got a sample size of 30. So right off the bat, I know I need degrees of freedom 29. I've got a sample mean of 40. That's my point estimate. I want a 95% confidence interval for the mean. So now I've got what I need to know. I find 95 and 29. I get 2.045 as the t-score. I plug in what I know. Now I've got 40 plus or minus 2.045 times 8 divided by the square root of 30. If my math is correct, get 40 plus or minus 2.987. I'm only 95% confident that the true mean falls in that range. But I am 100% confident because I followed the 3 steps. I'm 100% confident that's the right answer. And I want you to be 100% confident on Monday you have the right answer. And then the third variation we had was proportions. Proportions was, the formula is little p, my sample proportion, x over n, times my z-score, my critical value. Again, for proportions, my t-score is going to come out of this table right here, times the standard error, which is the square root of the sample proportion, times 1 minus the proportion, divided by the sample size. All of that is under the square root radical. If you try to take p times 1 minus p, take the square root of that divided by the sample size, you'll get the wrong answer. So make sure when you do the calculation, it's all under the square root radical. And that gives you the confidence interval for proportion. We looked at correlation and regression this morning. Correlation simply measures the strength of the relationship. -1 to +1. The closer it is to -1 or +1, the stronger the relationship. Closer it is to 0, the weaker. At 0, there's no relationship. There's no causation assumed. I'm just establishing a relationship. If it's very strong, very close to 1 or -1, now I can assume some causation and use regression analysis. That's that line formula we learned in geometry, y equals mx plus b. Use that regression analysis to make a prediction or a forecast what happens to the independent or to the dependent variable based upon changes in the independent variable. So I'm just trying to make some forecast using regression analysis based upon that relationship. And then we looked this morning also at hypothesis testing. We looked at the null hypothesis, H sub O. My claim, whatever the claim is in the research, that's the null hypothesis. I'm going to do my research, try to prove or disprove that somebody else's work was right or wrong. The alternate hypothesis, the H sub A, is the opposite. Whatever's in the null hypothesis, just the opposite in the alternate hypothesis. Then I'm going to test it. A type 1 error is where I have a true null hypothesis and I reject it. A type 2 error is where I have a false null hypothesis, but I accept it. I always assume the null hypothesis is true until I prove otherwise. And we looked at an example this morning of testing my hypothesis using the confidence interval. I get my claim from the previous research or from somebody's product claim, this car gets 19 miles to the gallon. I do my testing. I get my sample mean. my sample standard deviation, I get my sample size, I get my t-score, I develop my confidence interval, and if the claim falls within my confidence interval that I calculate, I accept it. If the claim falls outside of that confidence interval, then I reject my null hypothesis. That's what all I really want you to know about hypothesis testing. How to construct a null hypothesis for mean or proportion. It's either going to equal to, greater than equal to, less than equal to. The alternate hypothesis is if it's equal to, it's got to be not equal to. If it's greater than equal to, it's got to be greater, it's got to be less than. If it's less than equal to, it's got to be greater than in the alternate hypothesis. And I just test it. I make a decision based upon the data that I've got. If anything in this review does not make sense to you after you go through this review, it gives you Friday afternoon, Saturday, Sunday to go through this review. If it doesn't make sense, ask somebody, get a hold of me, text me, call me, send me an email, get a hold of your TA, ask the question. Don't wait till after the exam to say, well, I had a guy last year who came to me and said, you know, the stuff on exam 1 and exam 2 didn't make sense to me. Well, when you're getting ready for exam 3, that's no time to ask that question. If it doesn't make sense before Monday morning, get a hold of me or get a hold of your TA, ask a question. If it doesn't make sense, you're probably going to mess it up on the exam. So read the questions carefully. Take your time. You may only be 95% confident that the mean falls in this range, but I want you to be 100% confident how to answer every single question we've talked about today. Have a great weekend. Stay focused. Stay positive. Stay healthy. See you on Monday at the exam.